Okay, so welcome. Today we're going to be looking at we're going to be looking at logarithmic inverses of exponential functions. We're looking at inverses of exponential functions. That title's wrong there. So let's have a little look at what we're doing. This is the logarithm function. So obviously we saw the logarithm last lesson, and we can set up a function like this one, which is the base logarithm function. Your base has to be a positive value, because if you think about it in exponential form, it's going to be b to the c is equal to x, and obviously this b can't be 1, otherwise it's not going to create an exponential function, and it can't be negative, because as you're going up with values of c which are non-integer values, it's going to create square roots. So if c was a half, it would create a square root, and that's not going to work. So obviously this has to be greater than 0, and it also can't be 1, and a can't be 0, otherwise the whole function just becomes f of x equals 0. But then we get a exponential function, and they look like this. So the logarithm has to be the inverse function to it. We see that there in the diagram. What's important to see for the inverse function is the idea that we saw last time, 2 weeks ago, where the domain and range switch. So this function goes through 0, 1, which means the inverse would have to go through 1, 0. This function goes through 1, 2, and we can see that the inverse is going through 2, 1. And we see it switches there. It also looks like a reflection in the line y equals x. So what's important to notice about this here is an exponential function. So as we go up, changes in input values are linear. So we're going up by +2 here. If this one goes up by +2, so we have a constant linear change in the input values, producing a constant proportional change in the output values. So this is multiplicative. This proportional output change, this constant proportional output change with a proportionality of ×2, it's a multiplicative increase using multiplication, whereas the other one's an additive increase using addition. It's a linear scale. So the exponential function has a linear input value and a proportional output value. So notice how the logarithm function therefore has to be spotted with the opposite. We have to be increasing proportional input values will produce a linear pattern in the output values, because the inputs are reversed. The domain and range get switched. So as the input values change multiplicatively or proportionally, while the output values change additively or linearly, with a linearity, if we wish. So let's use that and determine which ones of these are exponential, which ones are logarithmic, and which ones are neither. You can discuss in your pairs for 2 minutes. Right, so this first one, let's examine what we've got going on here. So we can see that this one is going up by +1. That pattern continues, make sure it continues all the way through by +1. We can multiply here by a half. We can multiply by a half all the way down. So which type of function is this one? Exponential. This is going to be exponential, and we have to reason why. Exponential, because use the phrasing input values and output values for this type of a reasoning. As the input values change at a constant rate? Input values change at a constant rate. Sorry, let me just include of +1. Always reference your numbers if you can for a reasoning. Continue.
The output values change at a...
The output values change.
When I said a constant rate, right?
I like proportionally.
Oh, yeah. Proportional rate of...
Proportion. With a, factor of 1/2. I'll put times by 1/2.
So can you say they change multiplicatively?
Yeah, you can say that they change multiplicatively. You could use the phrasing additively and multiplicatively. Let's try use those wordings for the next phrasing. If it is, which one is this? So what we got going up here? Plus 20, is it? Oh no, it's not. It's times 3, isn't it? So this is times 3, and again, yeah. And just check this one, yeah. What about here? Plus 10. So which type is this? This one is logarithmic, because should we use the phrasing additively and multiplicatively?
Yes.
It sounds cool. Judy, you gonna go for it? As the input values change additively. Oh. Multiplicatively by factor, let's quote the factor always. What was it? 3? By factor 3. Then, what was the rest of our phrasing?
Then the output values change additively.
The output values change additively by how much? By plus 10. Okay, how about the third one? What have we got here? So, what is this? Times 10? Times 10? Is it logarithmically? Oh, this is times 2, isn't it? Times 2 times 2. So this is neither logarithmic nor exponential. We can neither.
So only be both of those.
How could we, if we wanted to know what type it was or what it might look like, what would be the best strategy at this point for us to use? Using what? How would we graph it? But we don't know the formula. In what type of a graph? Scatter plot. Scatter plot. I would enter the data into the calculator, do a scatter plot, and look at the shape and go, oh, wait a minute, and then you might see what type of pattern this one is. Yeah, scatter plot. All right, but in this question, we're asked to find whether it is logarithmic, exponential, or neither. So it is neither, so that is the correct answer for the question given. All right, how about this one? What are we going up by here? Times 2. Does that continue? Yeah. And we are adding -3. So it's still additively. We're adding -3. We can, but do we use the word subtractively? No, we use additively. Additively by -3. Generally, it's better to only have sort of two mathematical operations, multiplication and addition. So for division, you just turn it into a fraction, and addition, you just turn it negative. We got two mathematical operations. So you only need two identity numbers, 0 and 1. Let's just answer for this one that it was, what did we say? We said logarithmic. I'm not going to give the reason. We've got two reasons there, which gives you some examples of how to give a reasoning in such a question for your exam style questions when we come to them. If you write one of these type of responses in a test to one of these questions, you'll get the full marks in the end. Sorry, what do you say? You'd lose marks. You wouldn't get the same question with the same answer in a test. I don't think they're going to have two patterns that are both logarithmic. Generally, you do need to give a reason. For this type of a question, I would always give a reason. You have plenty of time, and it's good exam practice to sort of give a reason for this one. I would like the question to say and justify. I said it in my goals for today. If we look at what today's goals are, you can evaluate and justify.
I feel like that question would be too short to be a full FRQ question.
It wouldn't. It would be a part of several steps, but so it would definitely be a typical FRQ type question if you were to have a major coming up at any point soon. Oh yeah. But then you might go on and find the function and then use it, or then find the inverse. All right. So exponential and logarithmic functions are inverses of each other, which means it has to satisfy this definition for inverses that we've seen previously. So typically what you need to do is, if we draw a graph of an inverse function, they're going to be a reflection in the line y equals x. And the best way to do is to determine points is to take any point on the original function, reverse the domain and range, and then you've got points for the inverse. So in example 2, we are going to let f of x equal 3 to the x and g of x equal log base 3 of x. And I'm asking, we have to show that f and g are inverses. So we can't use the property that they are an inverse in order to make this proof. Let's do left-hand side is equal to g of f of x, which means that is equal to g of 3 to the x, which means that is equal to log base 3 of 3 to the x. Okay, short of just using notice in the question, it says that we have to show that they are inverses. If you notice in the question, it says show that they are inverses. So we can't just simplify down to x here at this point, because that would be using the property of them being inverses to make the proof. You can never use something in the proof to make that proof. If we are trying to show they're inverses, we can't use the property that they are inverses to show that they are inverses. But what else could we do? Great idea. Great idea. That's what I'm looking for. So lean goes down in history and glory. Now, what can we do here to simplify it? Log 3 of 3 is 1. So we can use the property. If you want to add in a property into your proof and explain what you're using, put it inside a little square box like this, so it's not part of the actual algebra. We can use the property log 3 of 3 equals 1, which means that this expression simplifies to x times 1, which is just x, which equals the right-hand side, QED. Sorry, I think my handwriting got smaller and smaller as I went across. My zoom went too big. Any questions on the proof there? This proof, the important thing to understand in this proof is the movement from this can't go straight to that, because in order to make that, you have to use the property of the inverse property of these two functions. But that's what we're trying to show. So you can't just make that simplification. You have to go through this other step.
Sir,
Yeah.
are we able to move it?
How are we able to move the x? Well, we're using the rule. It's one of the laws of logarithms. Log base c of a to the b is equal to b times log base c of a. It's one of the laws of logarithms. Let me remind us of the three laws of logarithms. What are the other two?
C is equal to 1.
So for the rules, let me leave off the c. We don't need that because it is for any base. So that's the first one. The second law of logarithms, log of x plus log of y is equal to what? Log xy. Log of x, what is the next one? Minus log of y is equal to what? Log x over y. So these are the three laws of logarithms. That first one is the most useful one. No, these are some of the properties of logarithms. They're very useful as well. To remind those from last time. They're not the laws, they're not algebraic, they're just sort of definitions from within. Let's add the change of base one as well. So log base c of 1 is equal to 0. Log base c of c is equal to 1. And log base c of x is equal to what? Well, we can write this in any base as log of x over log of c. So if you wish to change to another base, you can change to any other base. Zinedine. Shh. If we wanted to change to base b, we could change to base b like this. So these two here are just useful facts about logarithms, common properties. And then this is another rule used with logarithms. So it's a change of base formula. This one's called change of base. These are properties. And these are laws. This is the change of base formula. All right. Yes, it is. Yes, many people answer the same question. Okay, let me move on. So a portion of the graph of the exponential function k of x is a half times 3 to the x is shown in the diagram below. Find the inverse and then sketch the inverse. So let's have a go at finding the inverse first. So we have the function k of x is equal to a half times 3 to the x. So switch the domain and range to make the inverse relation first. So we can say that x is equal to a half times 3 to the y. And then we need to rearrange to make y the subject. What should we do first?
You also reverse the limit notation.
No, in the end, we'll write it as an inverse function.
Okay. So
So we just reverse the domain and range.
Okay, so you don't do anything other than the notation. So let's see where the inverse of the graph is going.
They will change. So if you have a vertical asymptote for one function, when you find the inverse, it'll become the horizontal asymptote. Yeah. For rational functions, particularly. All right. What should we do first here to get y on its own? Multiply by 2? Let's multiply by 2. We get 2x is equal to 3y. Which form is this in? This is an exponent form. So if we switch it to logarithmic form, what would we get? What's the base of the logarithm? Logarithm base 3 of 2x equals y. So therefore, our inverse function is k inverse of x is equal to log base 3 of 2x. Now, when it comes to sketching it, I wouldn't actually use that. Look at your graph here. Which points does it go through that we can read off nice and clearly? So we go through this one, which is 0, 0.5. Any others? It goes through 1, 1.5. We don't really have any others, but let's plot those two now. So we need to switch the domain and range, and we have 0.5, 0. So that's going to be there, 0.5, 0. And we're going to get 1.5, 1. So is that here? We get 1.5, 1. And then the graph, notice the asymptotes. So we have a horizontal asymptote here. We have a horizontal, well, a little bit higher up than that, yeah? So we're going to get a vertical asymptote here. We're going to get a vertical asymptote there. So showing that asymptotic behavior, this is the asymptote x equals 0. And this is the horizontal and y equals 0. It's part of the graph. We should include it. Show the behavior, go through those, and then it's going to head off in this direction. So this is how the inverse function, how to sketch the inverse function. You don't actually need to use that. But as you sketch more inverses or more log functions, you'll start to understand how the basic shape of the graph looks. The best place to start is with the vertical asymptote, which, if there is a horizontal translation, moves left and right. So look for a plus or minus inside the bracket if you have x plus, x minus c, it's going to move c to the right, and then start by plotting the vertical asymptote first. Then figure out where the point 1, 0 shifts to. So this will shift to 1, c. Sorry, I've written that wrong. This will shift to c, 0. It will pass through that coordinate. All right. Answer what you think it is. So example 4. Can we just stay on this one a little bit more? Yeah. No. The exponential function h of x equals a to the x contains the 2 points. Find the average rate of change of y equals log a of x over the interval 3 to 7. So if the exponential function goes through these 2 points, then the function y will go through what points? Give me 2 coordinates that this passes through. 3, 2. And 27, 6. Why does it pass through this? Yeah, firstly, the obvious thing that we need to state is we can see that the function y is the inverse of the function h. It's not given in the question. It's pretty obvious straight away that this is the inverse of it. So then we can switch the domain and range. So if we want the average rate of change over that interval, it's going to be y2 minus y1 over x2 minus x1. So y2 would be 6 minus 2 over 27 minus 3. So 4 over 24. Is that 1 over 6? Is that 1 over 6? Yeah. Okay, last question for today. Exam style question. Discuss with your partners. I'll give you 3 minutes for this one. The last question. Okay, so in order to answer this question, what I would recommend we do is read off some values. This goes through 0, 1 here. It goes through 1, 2. So let's make a table of values now. This goes through 0, 1, 1, 2. And we know what type of function is this? This is exponential. So the input value should be what? Additively or multiplicatively? So the input is +1. So the output has to be multiplicative. What is the multiplicative output here? Times 2. So looking at these tables, they go up to, well, anything with a 2 and a 4, that's not going to be any good, is it? Because we know that for our inverse function is going to have the x and y values that go 1, 2, and 0, 1. But we also need to get up to, was it 5? Yeah. So let's see if we can get up to 5. 1, 2. So this one is going to get up to, let's get it up to 4. So if we times by 2, we'll get 4. And then 8, 16, 32. And we were going to go up here as 1, 2, 3, 4, 5. So we have 32, 5 and 4, 2. Let's have a look. Does that match with any? 32, 5, 4, 2. So it's D. Okay. All right. We are finished there for today.